Today's lecture is going to be based on the so-called concentration inequalities. We mentioned a concentration equality last class, and this is the most basic concentration inequality. And in this class, we're going to make an improvement on it. Let's recall this is the most basic concentration inequality. We're going to assume that x is a random variable and that x is non-negative. More generally, you can assume that x is non-negative, and then you would say almost surely. That just means that the probability of the event where x is negative happens with probability 0. So that's how you can be a little bit more general than that. In probability theory, we usually talk about things being almost surely. Very similar in real analysis when you say almost everywhere, but in probability theory you say it like this. So you could also allow it to be negative, but the set of points where it is negative gives you an event of probability 0. But I'll just write this. Like, you should understand that in probability theory, anytime you're dealing with a random variable and you write something like this, in almost every case, you mean that you allow the set of exceptions to occur with probability 0. So this is the only thing we assume. And Markov's inequality would say that the probability that x is greater than or equal to some number t. Now, here's the picture. Here is the real number line. Here is 0. And we are assuming that the random variable is non-negative. So the random variable lives on the right side of the number line. And somewhere we have expectation. If the expectation is infinite, then there's nothing to say. Then this inequality is going to be trivial, as you will see. But if the expectation is some finite number, let's say right over here, this is the expectation, then we expect the random variable to be somewhere around that number. And we're saying, well, what if we introduce an arbitrary cutoff point t? Let's say, for the sake of a picture, that t is on the right side of the expectation. So this is the expectation. And we're asking, what is the probability that we end up in this tail? So we call that a tail. We're not supposed to be here. We're supposed to be somewhere around the expectation, especially if this t is a large number, substantially larger than the expectation. And Markov's inequality says that the probability that you're in that tail is bounded by the expectation of x divided by t. And this is a very general inequality because you do not assume anything about the random variable other than it's non-negative. And of course, if the expectation happens to be infinite, then of course this is true. Then there's nothing to prove. So this is the most basic of the concentration inequalities. It is describing how much a random variable is concentrated at its expectation where it's supposed to be located. The larger you make this t, the further you move away from its expectation. And as you can see, the probability diminishes, and this gives you a bound by how much it diminishes by. Now, you have to understand that because this inequality is so general, right, it works for any non-negative random variable, it is not surprising that it might not be tight. And tight means that the right-hand side that you're using to estimate the left-hand side can be substantially bigger than the left-hand side. So allow me to illustrate. It could happen, for example, that maybe for a specific calculation, the probability of this is 0.02, but when you use Markov's inequality, you're getting 0.85. So as you can see, or it might even happen that in a funny case, it could happen, for example, if the expectation is 100 and this is like 50, then this side is bigger than 1, in which case you're not really getting any information because you already know that this is bounded by 1. But let's say you're getting something useful. I mean, if you want to, you could say, like, you could, of course, say that it's bounded by the minimum between 1 and that expectation, because probability can never exceed 1. So, but let's say let's say the expectation comes out to be 0.85. Okay, so as you can see, if those are the numbers, this inequality is what we say not tight, that this number is substantially smaller than that number. And if you want to make this inequality tighter, then you have to assume something extra about x. And then you can improve the inequality. But that's often the way it works, that the more general something is, the less tight it's going to be. If you want to make it tighter, then you need to know some additional properties about the random variable. And this is what today's class will be about, how you can improve Markov's inequality for random walks. Because after all, we're dealing with random walks. So we have a very special type of random variable, and we're able to exploit it. We're able to take advantage of that, and we're able to therefore improve this inequality. So now let me say a quick recap from last class. So a quick review from last class. We have a sequence of independent coin flips, but instead of coding them as 1 and 0, we're coding them as plus or minus 1, and each of them happen equally likely, so heads and tails are equally likely. And then we construct a random walk that starts at 0 as this sum. So sorry about that. We construct W0 to just be 0, so that's the constant random variable, and then Wn for n bigger than 0. We then define it to be W0 where you start, and then you add independent coin flips, and that gives you a random walk with n steps, where W0 just indicates where the random walk begins. For simplicity, we assume it begins at 0, but more generally, of course, you could make it start at an arbitrary integer s, but we're just going to assume it begins at 0. So this is your random walk, and the random walk, this sequence, this is a stochastic process. A stochastic process is just a sequence of random variables called a random walk. Like I said, you can also call this a stochastic process because it is, after all, a sequence of random variables. But it would be a little bit silly to call this a stochastic process because, I mean, you could say that. It's just that every one of those x's is independent of the other one. So they have no influence on each other, whereas this is a little bit closer to what we want to say about a stochastic process, is that as n increases, as time increases, the way it evolves depends on the previous locations of where you are in that random walk. And this is what we did. We said that if we define an to be the sum of the first n outcomes divided by n, and the way this is related to a random walk is that this is just Wn divided by n. And you can think of this as the empirical average of n tosses, coin tosses, where the coin tosses are coded with plus and minus 1 for convenience. So it's the empirical average that you get after n tosses. So the sum of them is by definition Wn divided by n. And the law of large numbers says that for large n, that an is approximately equal to 0, and it's supposed to be equal to 0 because if these are fair coins, then the number of heads and the number of tails should be roughly the same, and so their difference should be around 0. So the average of everything that you get should be around 0. So this is what we expect if n is large, but of course there could be some margin of error. So to make this precise, we're going to use the weak law of large numbers. And remember what I said, the strong law of large numbers is more of a mathematical idealization, whereas the weak law of large numbers is a bit more practical of what we want to say, because in real life we only work with a finite amount of data. The strong law of large numbers is the idealization if we had an infinite amount of data points. So the weak law of large numbers says this. It says that for any epsilon bigger than 0, if we were to calculate the probability that an, so an is supposed to be around 0. So here's a picture. Here's the number line. Here's the number 0. This is where we're supposed to be. But we create a little margin of error, epsilon. So we create this interval. And whatever an is, we expect that an, if n is a large number, should fall somewhere within that small interval that contains that small margin of error. It should be here. It is possible that it falls outside, but the probability of it falling outside should be very unlikely to happen. So the way we say this is the probability that an is greater than or equal to epsilon. And I should say there are some authors who might use a weak inequality. They might write it like this. Not that it really matters. I'm going to write it like this. So the probability of this as the limit when n goes to infinity happens with probability 0. So if you fix the if you fix the epsilon and you start calculating these probabilities, in the limit, they will go to 0. That's what we're saying. So this is precisely what we mean. This is one way to make it rigorous. What we mean that for large n, that the empirical average of the random walk is approximately equal to 0. Now, let's quickly go through the proof of this again. The proof is actually very simple. So here's a quick recap of the proof. So to prove this, and the reason why I'm going through the proof again is because the idea behind this proof is going to come up in an example that we're about to do. And you're going to appreciate concentration inequalities more if we go through the proof again. So to prove this, we're going to rewrite this condition by using squares. We're going to eliminate the absolute value, and we're going to square both sides. So we're going to say an squared is greater than or equal to epsilon squared. And then this can be written as, I'm going to actually do this a little bit differently. I know that in the previous lecture, I used the variance. We used the variance to do this. I'm going to do this without using the variance. It's really the same thing. You have to recall what an is. An is 1 over n, and it's the sum of these coin tosses. So we're going to replace an by the sum of the coin tosses, and then we'll take this fraction 1 over n, we will square it, and we'll move it to the other side of the inequality. And so we end up with the sum of squares being greater than or equal to n squared epsilon squared, like this. That's what we end up with. And now we're going to use Markov's inequality. Whatever this is less than or equal to, here we're using Markov's inequality, that this is going to be bounded by the expectation of that sum divided by the tail. Okay, and then what happens next? Well, now you have to open up this entire expression. And part of the reason why I'm doing it, because I think the proof is more elegant when you do it without the variance. We did something very similar in the previous lecture where we raised something to the power 4. If that caused confusion for you, hopefully this will remove some of that confusion if you understand it in the simpler case. So here when you open up the parentheses, you will have x1 squared plus x2 squared plus xn squared, and then you have twice all of the cross terms. So you will have xi, xj, like this. All of these different combinations. But here's the whole point. When you start calculating the variance, here's what's going to happen. x1 squared is really just equal to 1, because each of these random variables is plus or minus 1. And when you square them, they will always be equal to 1. So their squares are all identically equal to 1. So you have the expectation of 1 plus the expectation of 1 plus the expectation of 1, a total of n times, because you have n terms over here. So that's how you get n. 1 plus 1 plus 1 n times. That's how you get n. Now for the cross terms, you get something that's very interesting that happens. So for the cross terms, if you take the expectation of their product, you get the product of their expectations, because these are independent coin tosses. Expectation is multiplicative when you have independence random variable. Remember, basically what independence means symbolically is to multiply, right? That's essentially independence. Independence means multiply. So the expectation of a product is the product of the expectations, and the expectation of xi is 0, and the product of xj is 0. So those ones contribute 0 for you, and you end up with n divided by n squared, and in the end you have n over epsilon squared. So that is the bound. And now you can see that this number goes to 0. You can make this number be arbitrarily small. Oh, I'm sorry. N divided by n squared. It should be the other way around. It should be 1 divided by n epsilon squared. This is what you end up with. And in the limit, that goes to 0. So basically, we have the inequality that the probability that an is greater than or equal to epsilon is dominated by 1 over epsilon squared times n. Now, as you will see, so this inequality is correct, but as we will see, this inequality is very rough. That's the opposite of being tight. And we can make it tighter by putting in more work. So this is true, but you can really improve that inequality. And we're going to do some examples where you're going to see that what we're getting over here is substantially bigger than what we're getting over there. You might ask, why does that even matter? Like, why do we even care? I'll show you an example of why you would care about something like that. But if you're wondering, why did we prove it like this? Why not prove it in a tighter way? Well, because when we proved the law of large numbers, we proved, so the reason why we proved the law of large numbers in this way is because we proved a general law of large numbers for many different situations, not just random walks. Okay? So where we're not proving it for just random walks, we proved it a lot more generally. So let me quickly remind you what we proved. When we talked about the weak law of large numbers, we made the assumption that these random variables were independent and they all had the same expectation. And we also assumed that they have bounded variance, uniform bounded variance. And from there, we're able to get the law of large numbers. So this is the best that we can do. It was not exactly this. There was some other bound in there as well. So it was not exactly that. I think there was like a B. I think there was a B over here. There was a B, which was the bound on the variance of all of them. But that's really the best we can do in general if we do not know anything else about our random variables. But because here we're working with random walks, we're able to exploit that and really improve upon this inequality. And that's going to be the idea. And that's what we call the concentration inequalities. Now, before we go into the concentration inequalities, I would like to do an example first that will illustrate why you want to have tighter bounds. So let's do that first. Consider the following example. Now, before we say what the problem is, we have to understand that we expect that an, so this is the average of n coin tosses. You can also say it's the average of the random walk, because it's the random walk divided by n, to be approximately 0, as we've said. So let's ask this question. How big should n be so that we are, let us say, 99% confident that an is somewhere between 0.1 and negative 0.1. So let me repeat the question again in the way that will hopefully make it easier to understand what we're asking. So here's the number line. We expect that we should be at 0. Now, of course, as we have remarked, that even though 0 is the most probable outcome, when n is an even number of steps, it's the most probable thing to happen, but it still happens with a small probability. So we could be a little bit to the right, we could be a little bit to the left. So we create a small margin of error between 0.1 and negative 0.1. And if n is sufficiently large enough, then we can expect that we will land somewhere in that interval. Maybe we're on the right, maybe we're in the left, but we're somewhere within that interval. And we want to be 99% confident, so this just means the probability is at least 99%. That's what that means. You can measure how confident you are in something by using probability. So that's what we're asking. Now, when you see this question, the first question you can ask is why, like, what is the motivation behind this problem? And really, what this question is that this is a problem, and you can even say this is like the most basic type of problem in a subject that's known as statistics. Now, what exactly is statistics? It often gets confused with mathematics because math gets used, but math gets used when you build a bridge. We would not call building a bridge mathematics. You're rather using math as a tool to help you build a bridge. So what exactly is statistics? I did mention it on the first day of the lecture, but hopefully that we have a bit more background in probability theory. This is the way I like to think of statistics. This is inverse probability, or you can say probability in reverse. Now, what do we mean by that? Well, what we mean by that is, in probability theory, you are given all of the information. You're being told what the sample space is. You're being told what the probability measure is. You're being told what a random variable is. Sometimes maybe the sample space is hidden. You're just given the probability density function of the random variable, but that's basically the same thing. So you're being given the probabilistic model that describes the random experiment. Whereas in the subject of statistics, something very different is going on. You rather have the data. The data are the outcomes associated with a random variable. So you have the data. You do not have the probability model. You rather just have the data. And your goal is to try to come up with the most plausible explanation from where the data came from. Now, to give you a more concrete example of what we're doing, and this is basically what we're asking here. So the above question, the above problem, is a special case of what is known as polling. And polling is when, and you probably all know this, it's when you want to know what percentage of the population has a certain property. So, for example, you can ask, what percentage of people are right-handed? Right? That's something you can ask. What percentage of people are right-handed? Well, we know from experience that the amount of people who use the right hand is substantially larger than people who use the left hand, but we want to get a number on that. So the most reasonable thing to do is we go out and we find people. So let's say we poll 100 people, and 80 are right-handed and 20 are left-handed. If a person happens to use both of their arms, maybe you, in those rare cases, maybe you just ignore that person. You only are interested in people who exclusively use one arm. So if you come across someone who, let's say, unfortunately lost both of their arms, then that would not be an appropriate question to ask. So you would not consider that part of your population, of your polling population. You see, the problem is that there is billions and billions of people in the world. And the only accurate answer that you can get to this question is to ask every person in the world that question and find out where they fall into. The problem is that's not doable. You cannot do that. So rather what you do is you do a random experiment where you pick a person at random and in an independent way, perhaps whether someone is right-handed or not is genetics, so you're not going to ask people from the same family if they're right or left-handed. You're going to have some method. Maybe you just take random telephone numbers or something like that, but you pick people in an independent way, and you get 100 independent people that have nothing to do with each other, and you just ask them which of these two is applicable for them, and this is what you find. So you can estimate, right? We would estimate that, let's say P, which is the true percentage, this is the mysterious number that we're trying to find. The true percentage should be around 80%. Because you can see that 80 out of 100. But there's going to be maybe a margin of error. That maybe we got a bit too lucky with people who are right-handed. Maybe that number is closer to 75%. Or maybe we got a bit too lucky with people who are left-handed. Maybe that number is closer to 95%. And that's really where the issue comes up in statistics, that you're doing a random experiment, but you do not know what the P is. Whereas in probability theory, like for example, what we're doing with these random walks, we know it's a perfectly fair coin. Whereas in this polling question, the chances are it's probably not a perfectly fair coin. Instead of heads and tails being equally likely, you can think of right and left as being heads and tails, and maybe one of them is more favored than the other one, and you're going to look at your data, and you're going to come up with the most plausible conclusion. Now, the most plausible conclusion is just to just take the ratio of the numbers, and that's how you get 80%. But the problem is there's a lot of uncertainty. Like, we understand it could be 80%, but let's say we make a margin of error. Let's say we make here we're using 10%, but let's say we use 2% margin of error. We might ask, are we 99% confident that the true percentage that we're trying to estimate falls somewhere between 82% and 78%? How confident can we be? And if we want to get the answer up to 2 percentage points, and we want to be 99% confident that we're doing this correctly, how many people should we poll? Is 100 enough? Do we need 1,000? Do we need 5,000? How many people do we need? And then, when the question is phrased in this way, then suddenly you begin to appreciate this type of a problem. Now, this problem is easier in the sense that these are fair coin flips, but you can easily generalize the problem where you have unfair coin flips. And once you understand how to approach the question above, the solution to that question would actually be very close to the way you would solve a problem like this. So this is a problem in statistics. As you can see, this is inverse probability theory, where this P, which dictates the way the random variable behaves, is hidden from us. We do not know that. Rather, what we have is we have the data, and we're going to use the data to try to make reasonable conclusions about what the P is. So we're really doing probability theory in reverse. And now, maybe I should say this about the field of statistics. People sometimes get confused by this. So some courses in a college are called probability and statistics. And the reason why they're called that way, like maybe you're taking a very intro level course and the course is called probability and statistics. Maybe some of you even taken a course like that. And what they're doing in the course is, when they talk about probability theory, is you basically learn about random variables, and this is mainly the normal. You learn about what a random variable is. You mostly learn about the normal random variable. Then you learn how to calculate probabilities associated with the normal. Like, for example, if you have a normal of mean 3 and variance 5, how do you calculate the probability that it falls between 1 and 2? So you learn how to do that kind of stuff, how you would do it on the calculator and things like that. In the old days, they used to talk about how you look it up in the table, but I'm not sure if anyone ever does that anymore. That's way too outdated. So that's like the probability part of the class, and then that's like the first half of the class, and then you get to the statistics part of the class where you're given the data, and then you try to say something about it. And this is what you care about when you're doing science. In science, you gather the data, and then you want to be able to say something about the data, but that's why they do the probability theory first. They want you to know a little bit about probability theory before you reverse the process. And there's another type of course. So many students in applied mathematics often take a course called mathematical statistics. And what exactly is that? Well, mathematical statistics is what you basically do is you solve various statistical problems. Like, for example, the problem that we just presented below, that's the polling problem. But there's many other commonly occurring statistical problems that come up quite often in science. So you solve various problems and develop the math, right? And solve the equations and all that. So you actually focus on the math. So there's this emphasis on the word math. So it's a course in statistics, but it really is, right? This is really a course. It is really a course in probability theory. Like, after you're comfortable with probability theory, there's many different things you can do with probability theory. You can go off and focus on stochastic processes. That's something that we're doing right now. Or you can focus on statistical questions, but you need to understand probability theory quite well in order to be able to do that. And that's what you're doing in that course. You're taking your knowledge of what you know about probability theory, and you're setting up various problems in statistics in a probabilistic framework, and then you're solving them, and then you get the equations, and you get all of that. Now, here's the part which you might find rather interesting. So continuing with courses. So often students of science are required to take several statistics courses. This is common in psychology. I know that in psychology, they make students take lots of statistics courses. And also in economics. Some people might take issue by calling it a science. But the way psychologists and economists, the way they justify what they're due to be a science is that it's not like a traditional science field where you can do very careful experiments. Rather, what they do in psychology and in economics, and this is why they call themselves a type of science, it's not like a traditional type of science, is they gather data for the claims that they make. So in economics, you would gather data for one idea, and then you gather data for an alternative idea for the opposite idea, and you kind of compare the two data sets by using statistics as a way to justify the claims that you're making. It's not like a traditional type of science where you keep everything identically fixed, because in the real world you cannot really do that, so this is really the best that you can do. So they're required to take several statistics courses, and interestingly enough, very common, right? If you go to graduate school in science, you have to take graduate courses in statistics. If you do biology, so for example, if you do biology, if you go for like a PhD program in biology, you have to take something called biostatistics, which is, as the name suggests, it's a statistics course specifically geared to the kind of statistical questions that a biologist often comes across. Now, you see, it's a graduate course. So you may wonder, how much math do you really need? Do you need to know probability theory? Do you need to know all that measure theory stuff? Do you have to know calculus? Because it seems like if you need to know that, is it really true that someone who's doing a graduate course in psychology really knows all that probability theory? No. And interestingly, so people in science learn how to think statistically, in fact, better than mathematicians. Mathematicians are quite bad in statistics. Using myself as an example, I've never heard the word standard deviation once when I was in graduate school in math. It's only when I was forced to teach statistics in some form or another to undergraduates that I had to use it. So mathematicians actually think very poorly on the level of a statistician, but people in science, they learn how to think statistically, and the calculations are all done by a computer. So the computer has various formulas, it has various algorithms for doing those computations, and the calculations, like, these calculations, that's what we call mathematical statistics. So that's something that's been worked out by mathematicians, and it was put onto a computer by programmers. And in real life, people who are doing science, they never actually have to do the math. You just have to understand what kind of statistical problem you have, what kind of statistical test you have to do, how you actually put it on the computer, what kind of feature in the software you have to apply. You get the numbers, how to interpret the numbers, things like that. You never actually have to do the math yourself. So the math has been done ahead of time. So I bring this up is because this question that we're looking at, you can argue, is the most basic type of question in the field of statistics. And that's like the motivation for what we're doing. So now that we have the proper motivation for the question, let's answer this question. So let's remove all of this. This is a distraction. And let's focus on the problem. So we want to find how big should we make this n so that our pole in this case, so in this case it's a pole which is 50-50. In real life it's going to be a bit more complicated than that because you do not know what the actual percentages are. But in this particular case, it's 50-50. It's equally likely to go to the right or to the left. And we're asking, we want to be 99% confident that the average of the random walk falls somewhere within that interval. So how would we figure this out? So what we want is when we formulate this question in the notation of probability theory, we're asking for the probability that an in absolute value to be less than 0.1, and we want this probability to be at least 0.99. Okay, that's what we're asking for. And so you can rewrite this by subtracting 1. So you can do, this is equivalent, so this is if and only if, so you can take complement. So you can say 1 minus the probability that an is greater than or equal to 0.1 is less than or equal to, you have to flip the inequality, 1 minus 0.99. So we want the probability of this tail to be outside that, so that's the probability of the tail, to be dominated by 0.01. Now, what we know from Markov's inequality is that this is dominated by 1 divided by epsilon squared times n, where this is what we call the epsilon. So the probability that an is greater than or equal to 0.1 is less than or equal to 1 divided by 0.1 squared times n. And what do we want? And we want this itself to be smaller than this number. Because, well, look at this. This is the level of confidence we want to achieve. So if we know that this quantity is smaller than 0.01, then certainly this tail is smaller than 0.01. And now let's solve this inequality for n. And that will give us the n that we need. So that would mean that n, if we flip the fractions over, we have to reverse the sign of the inequality. That would be n times 0.1 squared is greater than or equal to, so you flip that over, so that would be 100. So n has to be greater than or equal to 100 divided by 0.1 squared. So n has to be greater than or equal to 100 divided by 0.01. So that would be 100 times 100. So that would be 10,000. So that's what I'm getting, 10,000. Maybe, yeah, so that's what I have. Let's see. I'm just worried that maybe I made one of those mistakes where I have an extra 0. So it's dominated by this. So 0.1 squared. You flip that over, that's 1 out of 100. This is 1 out of 10, 1 out of 100. So 100 times 100. So that should have 4, 1, 2, 3, 4, 0. Okay, so that's what we have. If I made a mistake with an extra 0, that's not important because I'm trying to illustrate a point here. So what does this mean? So this means if n is 10,000, then the average, right, then the polling average is within 0.1 of the right answer. Now the right answer over here is 0 because the theoretical expectation is 0. You see, I'm intentionally writing it in statistical language because that's the way it's used in applications. People who are taking a statistics course, like people with a background in science or whatever it is, they never actually do these calculations. You just sort of learn how to set up the problem, and then the computer does the calculations for you. So here we're actually working out the math behind all this. So if you make n be 10,000, then the polling average, which is just referring to this, is within 0.1, so it's within 0.1 of the right answer with a confidence level with confidence of at least 99%. And the question that really matters, now if you're a mathematician, this really does not mean anything to you. But if you're someone who's conducting real life surveys, okay, so in real life, surveys cost money. Right? You have to pay people to go out there and find people and collect all of that. You want to use as few people as possible. So do we really need 10,000 people? Do we really need that many people? Is 1,000 people not good enough? So this is basically, so this is what we mean by tightness of the inequality. That how tight is this inequality really? Is this a massive overestimate? Because if this is a massive overestimate of whatever that probability is, then we do not need that many people. Maybe we only need 1,000 people. Can we make the number any smaller? So what I'm going to do next is I'm going to do this calculation for you using a computer where we get the exact answer, and we'll be able to compare with what the exact answer is to what we're estimating it to be by using Markov's inequality to further illustrate the point. Now what I realized, because I just tried to test it out on a computer, I realized the numbers, so we got that n was, so how big should n be? So we got that n should be 10,000 when we use Markov's inequality. And as you will see, I will do it, as you will see, this number is too big for a computer to handle. It becomes very impractical. This is actually another reason why you want to use concentration inequalities. But as you're going to see, trying to solve this problem exactly with the exact formulas for the probability is going to be very, very impractical. And I'm going to change the confidence level to make it a bit more practical. But for now, I'm going to show you how you would solve it. So this is what we're going to do. We're going to compute. So let us compute the probability that an is greater than or equal to 0.1, where n is 10,000. And if the inequality is tight, then this number should be close to 99%. Oh, I'm sorry, it should be close to 0.01%, right? It's the other side of it. It should be close to 0.01%. If this number is substantially smaller than 0.01, that means our inequality was very rough. Our estimate from above using Markov's inequality was very rough. Now, how do we calculate this? Well, let's rewrite what this means. So recall that the average, so this is going to be the probability. If you clear a denominator, if you multiply through by n, then you're saying that the sum, okay, this is just a random walk divided by n. So if you clear denominator, then you're saying that the random walk should be bigger than or equal to 0.1 times n. That's what you're saying. And how do you calculate the probability? So in this case, if you were to compute what the number is, in this case, n is 10,000, so it's 0.1 of 10,000, and 0.1 of 10,000 is 1,000. So you want the random walk to be at least 1,000. And the way you do that is you just sum up all of those values. So that would be the sum of every integer from 1,000 to the maximum probability, the maximum value that the random walk can take. So the maximum that the random walk can take is when they're all equal to plus 1. And since n is 10,000, you will go all the way up to 10,000. And then you will sum up all of those probabilities individually, where Wn is equal to this integer I. So this goes up to n. And then you do not forget, you have to multiply this by 2, because we're kind of doing it on one side and on the other side. We're just summing it from 1,000 up to n, and then we're multiplying it by 2 sides. And remember when we talked about how you calculate the probability that the random walk takes on a particular integer. So the way you do it is, this is coming from a previous lecture, it's 2 times this, I from 1,000 to n, and the probability the random walk is equal to an integer, it would be 1/2 raised to the n, and then it would be n choose n minus I divided by 2. You have to understand that in this case, because n is an even integer, if I is an odd integer, then the probability that the random walk is equal to an odd integer would be impossible. So those would just be 0. So you're only going to look at the ones that are even. So it goes from 1,000 to 10,000, but really you're skipping every other one. You're only looking at the even ones. And this is where the problem comes up. The problem is that 1/2 raised to the power of 10,000 is an unbelievably small number, but then it gets multiplied by an unbelievably large number. Because how do you calculate this? Like, how do you calculate this quantity? Like, it's n factorial divided by some other stuff. Can you imagine calculating n factorial when that's the number? You can try doing it on the computer, but even when the numbers get too big, the computer just returns 0 because it's the number, or 0 or infinity when it gets too big or something like that. So let me therefore illustrate how you would do this calculation using a computer. So let's switch screens, and you'll be able to do the calculation yourself. And then I'm going to make the numbers be smaller, so you'll get to see, so you'll get to actually get some sensible number, and then you'll be able to compare with the inequalities. So we'll go to R. We click File, New File, R Script. I'm not going to talk about the details of R. We already talked about it a few times before. I imagine that people who are following this know how to do this. We're going to set n. So this is, we're calculating. So what are we doing? We are computing the probability that the random walk, so an, is greater than or equal to, it's greater than or equal to, so the margin of error here is 0.1, and the confidence that we're using is, we want this to be less than, so we want to be 99% confident that it's within that interval, so the complement would be 0.01. So that the probability of this should be smaller than that number. That's what we're calculating. So how do we do that? Well, what we did is we write the average, the polling average, as the random walk divided by n. And so the probability that an is greater than or equal to 0.1 can be written as the probability that the random walk is greater than or equal to 0.1 times n, okay, like that. And then you can double it, because you can use symmetry, so you can double it. You can just say twice, and then you just look at the positive side of the random walk. Positive, negative, they're symmetric, equal probabilities, so you can double that. So here's the way you actually set up the code. You're going to write down what the n here. So here we said by using Markov's inequality, so n, how do you get n? N is equal to, so we have epsilon. Epsilon is 0.0. So epsilon, this is the margin of error in the polling average. So that was the polling average. Then confidence, this was our confidence, 0.99. This was our confidence. How much confidence do we want to have in our polling average? And then how do we get the n? So n was equal to 1 divided by, so it was 1 minus the confidence. It was this. It was 1 divided by epsilon squared from Markov's inequality, and then we had to multiply it by 1 over 1 minus the confidence. So the complement of that is 0.01. So now this is just written for ourselves. That's just human language, but this is what the computer reads. So if we run this and we check the value of n, is it 10? It is 10,000. That's exactly what we get when we use Markov's inequality. This was really Markov's inequality. That's how we end up getting 10,000. Now let's calculate this probability. So this is what we want to calculate. Well, we're not actually calculating. We are checking. We are checking that we're checking that the probability of this. Okay. So now we compute the probability 2 times the probability that the random walk is greater than or equal to 0.1 times n. So here's the way we do it. We have to sum up over all of those integers. So I'm going to write I is equal to, you're going to form a sequence of integers that start at, this is how they start. So they're going to start at 0.1 times n. It's going to go all the way up to n. And we're going to do by is equal to 2. So if you're not sure what that means, is this is the way you input that sequence of integers that you're going to be working with. So just to show you what it is, if you were to run all that part of the code, and then you would ask for the computer to display for you I would suggest instead of typing I, write head of I. So you just see the beginning part of the sequence, and that's what's happening. It's 1,000, 1,002. You're skipping every other one because the random walk cannot take on odd numbers in this case. If you look at the tail of I, you get to see the final values. As you can see, this is where you stop, and these are it's skipping every other one. So now here's how you find the probability. The way you would then find the probability is, this is what we were saying, it's 0.5, it's a half raised to the n, multiplied, you're going to choose, so choose n minus I divided by 2. By the way, you could also write this as n plus I divided by 2 because of symmetry, but I'll just keep it like this. And it's going to generate for you a list of numbers. So basically what you're doing is, because I is a list of numbers, you're just passing every number in that list, and you're doing the calculation for that integer. So it's going to calculate for you a list of numbers that you're getting, and then you have to sum over those numbers. Now here's where the problem is. If I do this calculation, you can see it's just nan. It's giving me nan because what's happening is that a half, so if you ask the computer to calculate for you 0.5 raised to the 10,000, the number is so small that it stores it as 0. And the other problem is that this choose number is so big. So let's ask it to do choose n. And the very first number that we have is what? What is it, 1,000 or something? Yeah, it gives you inf. It's not actually infinite, but it's so big that the computer just stores it as positive infinity. You can probably increase the amount of digits that it keeps, but then it begins to really slow down the computer. So you can see that even for an example as innocent as this, the numbers get so astronomically large that the computer cannot handle it. This is quite surprising, but as you can see. So let's make the numbers a little bit smaller. Let's make the margin of error, let's keep it as 0.1, but let's reduce the confidence. So let's make the confidence be 90%. Now, I know you can say that maybe in real life you do not want to have 90% confidence. That's not very high confidence, but let's not worry about that. In the field of statistics, you get to choose your own confidence levels for whatever you're doing. Maybe you do not necessarily care what the number is. You just want to be fairly confident that it's bigger than something else. So like you get to choose your own quantities that you want for something like that. So anyway, let's say this is what we have. What is n in this case? So n in this case is going to be 1,000. So this is a lot more reasonable. Okay, then we calculate I. This is going to be our sequence of integers, 1,000 of them. And then what we do next is we're going to go ahead and calculate what the probabilities for each of these. You can see these numbers are very small. This is 9.33, and this is 10 raised to the power negative 302. So some of these are really small. Some of these are more plausible, like these ones over here are more plausible. And it's just going to calculate these. It's going to sum these up. So you would just tell it to sum. This is the way you write it. You will tell it to sum those numbers, and you get a probability. Now you can see this is what you get. Now what did we want to get? What we wanted to get is our confidence level was 0.9. So what we really should be getting is 1 minus the confidence, so 0.1. So as you can see, oh, and I forgot to do one more thing. Sorry about that. I should have multiplied this answer by 2 because of the symmetry that we were saying. So let's just multiply it by 2. And you're getting 0.01, whereas this is what you're trying to get as close as to that as you can. This is the complement of the confidence. You're trying to get as close as you want to 0.1. And as you can see, you're substantially smaller than what that number is. So it appears that there's no need for you to use 1,000. Like 1,000, so in this case we're using, so what is our n? Our n is 1,000. It looks like 1,000 is too big to use. Let's make the n smaller. Let's say we were to set, so let's experiment with n. So this is what we get from Markov's inequality. This is what we get from, but let's experiment. Can we use 500? Let's just see. Can we get away with 500? And 500, so 1 minus the confidence is 0.1. So you can see that it's not smaller. No, it actually, no, that works. That works. So we can get away with 500, right? We're getting a number that's still smaller than 0.1. What about 200? Now with 200, that's too big, as you can see. With 200, we do not have the confidence anymore. Let's try 300. So it looks like 300, yeah, so it looks like 300 works for us. So it seems, right, so it appears the optimal value for n is about 300. So Markov's inequality gives us 1,000. That's an entire order of magnitude more than what it's supposed to be. So there's no need to use that many to get a 90% confidence on your polling average. It looks like you can get away with 300. Now, here's the thing. In this particular example, the numbers are small enough that you can actually do these calculations yourself and try to find what that optimal number n needs to be. The problem is, as in the example that we just did, if these numbers get too big, if these numbers become too big, then it's no longer feasible. Yeah, if these numbers become too big, then it's no longer feasible to do these calculations on a computer. You want to do something else. Like, of course, if it was possible to carry out these calculations, these very intense calculations on a computer, then you can brute force it. But you want to be able to do it in a better way, in a way that it's somewhat close to the answer, but it's more practical to do. And that's exactly what a concentration inequality is going to achieve for us. Now you can see on these Wikipedia page, they have some concentration inequalities, and they talk about the law of large numbers. And they give you different inequalities. So this is the most basic one. Then you have Chebyshev, which is a version of this with variance, basically the same thing. And as you go down, there's so many different inequalities here. One talks about the Chernoff bounds. Then there is something called Hofding's inequality, the Bernstein inequality. In fact, many of these inequalities I've never even seen myself. I'm seeing these for the first time. This just goes to show you how deep the subject of mathematics is, that there's just so many different types of inequalities that they have here. And so concentration inequality is a little bit vague because there's so many different types. They make different types of assumptions about your random variables, and that's why you have different types. But they all basically try to achieve the same idea, where you're trying to replace deviation from your expected value by tighter types of bounds. Now, let me give you some extra resources for those of you who might be interested in this. There is an entire course. So there's many different types. There's something called the Chernoff bounds. Then there's called the Hofding's inequality. I'm probably mispronouncing all of these names. There's Bernstein's inequality. And there's many, 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 but these are like the common ones that you see. And basically, in the special case of random walks, they lead to essentially the same inequality. These are just more general types of inequalities. Now, I found a very interesting video series. So there's something called the India Institute of something, or the National India Institute, and they have an entire course, and the name of the course is called Concentration Inequalities. So imagine that, an entire course dedicated to concentration inequalities. We just have a single lecture dedicated to these inequalities, but you can have an entire course on that. Again, it just goes to show how deep mathematics really goes. So if you're interested in that, you can look into that. I would say perhaps a more reasonable resource to look at, because you probably do not want to stop this course in the middle to go to a different course. Otherwise, you never finish. Maybe if you're interested after this course is completed to go and learn that material. But a more useful resource, which is not as it's not as extensive, is there is a book. It's a book that was very recently written, not that long ago. It's called High Dimensional Probability. Very recent, just a few years old. I'm not going to write the name of the author because I'm going to misspell it. Instead, what I'm going to do is I'm going to do something better. I'm just going to take you to the page of the author directly so you get to see the book. So let's go to the page directly. This way, I'm not going to misspell anything. This is the more honorable thing to do. So it's a book that was written in 2019. It was given awards, so that's very impressive. The name of the book is called High Dimensional Probability. You can look at the author. So this is the author, Roman Vershnin, professor of mathematics, and he has a copy of the book. And fortunately, this book is free, so we can just go here and see what that is. And if you go to page 30, he has an entire chapter dedicated to, so page 20, I should have said. He has an entire chapter dedicated to concentration inequalities. If you're interested in what the theme of the book is, the theme of the book is basically random vectors in high dimensions. So we talk about random variables that give you random numbers. Well, a random vector, as we saw before, it gives you a random point in high dimensional space. So it is a book dedicated to people who are working in the field of, let's say, machine learning, which they're working with random vectors in high dimensions. So he's written a book so people can learn the mathematics necessary for that. The nice feature about his book is that the author avoids the use of measure theory, which makes the book a little bit more accessible to a larger audience. So he has an entire chapter dedicated to concentration inequalities. And as he says, what is a concentration inequality? You have a random variable. You want to know how far away it deviates from its expected value. And he goes through some examples. And there's all sorts of inequalities over here. The one I want to get to, so he talks about the Hofding's, and there's many different types. But the one, let's see, the one I want to get to. So it is hidden somewhere in this book. But I'm going to show you somewhere else. Also, for those of you who are interested, this book has video lectures by the author. So the author himself created video lectures for you out of this book. So if you want to, you can look at lecture number 6. I think that's the correct one. If not, maybe it's lecture number 7 or lecture number 5, somewhere around that, where he works out concentration inequality. So he has a full video series dedicated to the book, and the book has problem sets. So I just bring it up. Maybe some of you are interested after this course is completed and you like the world of probability theory. That's a very interesting, exciting area of mathematics, and you like it and you want to explore more things. That's something you can look into for the people who are interested. You can look at lecture number 6. So I guess if you just search for high dimensional probability, and you probably will be taken to the video series directly by the author, and he explains it very well, by the way. He explains it very well. It's well made. It's not like PowerPoint. I know people do not like PowerPoint. It's written out like a traditional lecture. So you get to see that there. So the concentration inequality I want to get to, let's see if I can find it. It's a bit confusing which name it goes with. So on the Wikipedia page, the one that we want, again, different sources might call them something differently, but at least on the Wikipedia page, it's the one that they call the Bernstein inequality. And this is what it says. It gives bounds on the probability of the sum of random variable deviates from its mean. In the simplest case, this is the simplest case, that's what we're doing with random walks. x1 to xn are random variables taking value plus or minus 1 with probability 1/2. So this distribution is known as the Rademacher distribution, but not that it matters for us. And then it says for any positive number. Here they're using a weak inequality. Here they use a strict inequality. We're using a weak inequality with the, but it does not really matter. And this is how you can estimate it. It's 2 exponential function negative that. So let's actually put this. So this is the inequality. This is the improved inequality. So if you put in the value for epsilon that we're using, so our value of epsilon here is 0.1, and you set this smaller than the confidence level, then you get a much improved value for n. And notice you have a factor of 2 because of the symmetry. So let me actually solve that. I mean, you can solve that equation yourself, but I'll just solve that equation for you using Wolfram alpha. So the estimate that we have, it's 2 times the expectation of, so that's just e raised to the power of, and it's negative n times epsilon squared, right? That's how, in this case, epsilon is 0.1 squared. And then everything gets divided by 2 times 1. So I'll just write 2 plus, I'll distribute out the 2. So it will be 2 times 2/3 times 0.1. So that is Bernstein's inequality. And we want to make this less than or equal to our confidence. So 1 minus 0.9. So we want to make this smaller than 0.1. But instead of making it less than or equal to that, what I'm going to do is I'll just make it be equal to that because I'm trying to find the optimal value of n. And remember what we said, it's about 300. So I think I made a mistake with the brackets. I need an extra bracket over here. And we ask it to solve for n. So as you can see, it gives us that n is around 600. Now the optimal value is 300. So it's still not close to the optimal value. However, let's return back to the example that we did before where we got 10,000 using Markov's inequality. In that example, if you recall what the numbers were, instead of, so this 0.1, so this 0.1 is going to be 0.01 because we want 99% confidence. So that was the difference. We had 99% confidence. And the 0.1 over here is just the epsilon. That's the margin of error. So there, when you use Markov's inequality, you get 10,000. But when you use this improved concentration inequality, you get 1094. This is an entire order of magnitude smaller than what it should be. So this is a lot better. This is a lot better. So this says that if you have about 1,100 samples from your population, then your polling average will be within that 99% confidence level that you're trying to achieve within that interval. And with that, you immediately begin to appreciate why these tighter bounds are so valuable in these kinds of problems. So to basically summarize, this is what we're saying. So we will prove that if you have the probability that an is greater than or equal to epsilon can be improved by the following inequality. It's 2e raised to the negative power of, so I have to look this up, negative n epsilon squared over 2 1 plus epsilon over 2/3 epsilon. No. It's just epsilon over 3. So this exponent is not as nice when your random variable is allowed to take +1 or -1. This is the way that we're doing it. There's another inequality, which is just a modification of this, which is much easier to memorize. And it's when your random variable is 0 or 1. And then you would not say that an is greater than or equal to epsilon. You would rather replace this by an minus a half greater than or equal to epsilon, because now the expected value is going to be a half instead. But that's not the way we work with a random walk. And I believe, going off memory, I believe when you do it in this modified case, the way the inequality comes out to be, it's 2e to the negative n epsilon squared. So it comes out easier to memorize how it's supposed to go. But in this version, when you use plus and minus 1, which is the way we're doing it, that this is our random variables, then this is supposed to be, there's not supposed to be a negative there. So it's this, right? It's going to be this. So that's what we're going to prove. I'm actually not sure if we're going to be able to prove that. Maybe we can get somewhat close to that. We're going to just see what happens. We're going to start proving it. We'll see how close we can get to that. I'm just being a little bit cautious over here, because some of these inequalities that you see, that sometimes you can get kind of close to it with a decent amount of work, but if you want to radically improve it by putting in like an extra fraction in somewhere in the inequality, that might take substantially more work to get a bit more out of it. So I'm just being a little bit cautious here as we go ahead to prove it. So this is the goal. We're going to prove something like this, and this is what we call a concentration inequality. And if you look at the book, let me just show you. I want to return back to the book one more time before we start proving things. So if you look in the book, so this is the wrong one. So let me return back to the book. So when you go back to the book to show you this, so this is what I mean when you make assumptions. So the author talks about these random variables that are known as sub-Gaussian, whatever that means. You have to define what that means. So he actually gives you a definition. Then the following are equivalent, and that's what he calls sub-Gaussian. So he shows they're all equivalent. And let's just keep on going. So he has some kind of inequality here, general Hafting. So there's an inequality here for concentration. And as you can see, he says, let be independent sub-Gaussian random variables. So he is now putting an extra assumption about what these random variables are and getting an improved inequality that you get more so than when you use Markov's inequality. So that's the whole point. You have to assume something more about those random variables in order to get a tighter inequality. In our situation, it's going to be a lot simpler because we do not need to define what this is, because we have a very explicit random variables that we're dealing with, and we're just going to exploit that in order to get the inequality that we want. We will now derive Bernstein's inequality or any of the other equivalent names that it goes along with. As you can see over here, sometimes it's called the Chernoff bound and other types of inequalities. Now, what I find a little bit strange about the Wikipedia page is the way they write this inequality over here. And this is why I was confused earlier why this is the form that they write it. You will notice they have negative n epsilon squared divided by, then they have 2 multiplied by this. And the inequality that we're going to derive will actually be better. It will be tighter. Namely, if this, we're going to set epsilon is equal to 0. And by setting epsilon is equal to 0 in the denominator, you're making the overall fraction bigger. So you have a more negative exponent, which will mean that the actual function becomes smaller. So you're getting an improved inequality. So I am not sure why this is the form they write it in. What we're going to prove is something that I've mentioned earlier. So we're going to prove that the probability that an in absolute value is greater than or equal to epsilon can be dominated by 2e, and the exponent here is going to be, now I know I mentioned 2n epsilon squared, and I said this is what happens going off memory when the coin tosses are represented with 0 and 1. And then this is an minus a half. But in what we're doing, this is rather going to go like this. It's epsilon, it's n epsilon squared, and everything gets divided by 2. That's what we're going to prove, and this is actually better than the inequality that they have on Wikipedia, which I find confusing why they would write a weaker. Well, when I say weaker, I mean the inequality is not as good as what we have. So this is what we're going to prove, and what I'm going to show you is I'm going to show you the idea behind the derivation, and then it will be a homework problem for you to derive it yourself. So the first thing that we do in deriving this inequality, so we want to get an estimate for this probability. The first thing that we do is we take advantage of symmetry, and we're only going to get an inequality where an is greater than or equal to some positive number epsilon. This is why we have an extra factor of 2, because then by symmetry you also have the negative side. So that's the first thing that we do. The next thing that we do is we have to recall what this is. This is the random walk up to time n divided by n itself. It's the average of the random walk, which means that you can rewrite this in the following form. This is the random walk greater than or equal to n times epsilon. So far, it's something that we've seen many times. And now we're going to use we're going to do something very clever. This is a very clever idea that goes back to Chernoff. And when you first see it, it's not going to be clear why you're doing this. But basically, the first thing is we have to recall what Wn is. Wn is a sum of coin tosses. And the idea that Chernoff had was you want to replace addition by multiplication. Multiplication just behaves better. It's easier to work with. And furthermore, because these random variables are independent, when you have to take the expectation of their product, it will just be the product of their expectation. It's just going to work out in a nicer way. So you're turning addition into multiplication. And the way you do that is by taking the exponent of both sides. So it's actually similar to the way we proved the law of large numbers. So when we proved the weak law of large numbers, you probably recall that we squared both sides. When we proved the strong law of large numbers, we actually had to go to power 4 to get what we wanted to. Here, what we're going to do is we're going to take the exponent of both sides. But before we take the exponent of both sides, the idea that Chernoff had is to multiply through by a positive constant. So we're going to multiply by a positive constant. Let's call that constant, for lack of a better name, let's call it lambda. For some positive lambda to be chosen later. So this is the part which is a little bit ad hoc, like why would you do that? So that's the first thing that you do. And then the next thing that you do is you take the exponent of both sides. So then you will have that the probability of e raised to the lambda wn is greater than or equal to e to the lambda n epsilon. And now we're going to use Markov's inequality that we've used many times before. So this is less than or equal to, and this is Markov's inequality. So you've probably noticed that we never use Markov's inequality directly. We usually manipulate the inequality a little bit, and then we apply Markov's inequality. So this is what we're doing, but this time we're doing it with exponents. So by Markov's inequality, this is going to be the expectation of e to the lambda wn divided by e to the lambda n epsilon. We're going to explain how lambda is being chosen, but before we do that, let's work this out. Now, what is this? But the exponent of e to the lambda wn is the expectation of e to the lambda x1, e to the lambda x2, e to the lambda xn. Because by definition, a random walk is a sum of independent coin tosses. Now we use independence, that each of these random variables are independent of each other. And so we can write this as the expectation of e to the lambda x1, e of e to the lambda xn. And now we're going to compute these. So you're going to show, so let's calculate what this is. So to find what this is, we have to determine, we're trying to find the expectation of this random variable. So this random variable has only two outcomes, because x has only two outcomes, plus or minus 1. So there's only two outcomes, e to the lambda or e to the negative lambda. And they all happen with equal probability because this is a symmetric coin. So the expectation of this would therefore be 1/2 e to the lambda plus e to the minus lambda. And this one is actually going to be the same thing because xn, it is a different random variable, but it does have the same distribution. And so the probability that an is greater than or equal to epsilon is dominated by the following. So we found the expectation of this. So it's a product of expectation. Each of these is 1/2 e to the lambda plus e to the minus lambda. So this is 1/2 e to the lambda plus e to the minus lambda. And this appears a total of n times. So we have n such factors. And this gets divided by what we have in the denominator. And in the denominator, we have this. So this is e to the lambda n epsilon. So this is what we have. Now here's the idea. When we reach this inequality, the idea is to pick lambda to minimize this quantity. That's what it is. So you're going to choose this lambda to make this as small as possible. Because the point is, this inequality is true for every positive lambda. So to get the tightest possible inequality, you're going to pick lambda as small as possible. I'm sorry, I take it back. You're going to pick lambda in such a way so that this fraction is as small as possible. That will give you the tightest possible bound. Now, here's something that is a little bit problematic. So if we try to minimize this by using calculus, in other words, you set the derivative equal to 0, because that's how we minimize something, you differentiate it. You're going to treat this as a function that depends on lambda. You're going to differentiate it. The problem is we will get difficult to solve equations that are hard to evaluate. I mean, you can try doing it. And you can treat this as a homework problem. You can try to do this yourself and convince yourself that if you try to solve this directly by trying to find where the minimum is and what the minimum is, after you find the lambda, you put it in there to find what the minimum is. It's not so easy to then determine what that is. So it's better to replace it by something that's more convenient. And what you realize is that this function, that's actually what you call the hyperbolic cosine function. That's what that is. So if you've never seen it before, so cosine of lambda, when you write it into a power series, it's 1 minus lambda squared over 2 factorial plus lambda to the 4 over 4 factorial minus lambda to the 6 over 6 factorial, and so on. The hyperbolic cosine function, it's just like cosine, but it goes positive. I assume that you've seen this before. And it's not hard to show. That's the same thing if you were to take e to the lambda and you were to add to it e to the negative lambda and then divide it by 2. So it's 1/2 of that. And the reason for this is because e to the lambda is this series. So you have all of the powers of lambda. And e to the negative lambda, it's when you replace lambda by a negative. But when you replace lambda by negative lambda and you square it, the even powers will remain the same. And now notice what happens when you add these powers together. So if you were to add these together, you will have cancellation. So this cancels with this, the odd ones cancel, and you have exactly what you call the hyperbolic cosine function, except everything's being doubled, so that's why you have a 1/2 in front. If you've never seen this function before, just treat it as a definition, but this function has different appearances. It's called the hyperbolic cosine function because there's an area of geometry called hyperbolic geometry, and just like we have the law of cosines in Euclidean geometry, one has the law of cosines in hyperbolic geometry, except instead of having cosine, you have hyperbolic cosine. So that's the analogy with cosine. But other than that, it also looks very similar to cosine, except it has no alteration. So that's what you recognize. And then one thing you can say about hyperbolic cosine is we can replace the hyperbolic cosine function by e to the lambda squared over 2. Why is that? Well, let's write out e to the lambda squared over 2. So e to the lambda squared over 2, if you were to put it in there, so you replace lambda by lambda squared over 2, and then you will have even powers. So you would have 1 plus lambda squared over 2. Then we will have plus lambda to the 4 over 2 squared times 2 factorial. It's 2 factorial because you have to understand that we're putting this in lambda squared. And then when you put it into lambda cubed, you will have lambda to the 6th over 3 factorial 2 cubed, and so on. Now, if you compare cosh lambda and this function, you will see that they start off the same on the first term. They're the same on the second term. And on the third term, you have lambda to the 4, you have lambda to the 4. But here we have 4 factorial, but here we have 4 times 2. We have 8, whereas this is 24. Here we have 6 factorial, which is a big number, whereas here we have 6 times 8. So these fractions are smaller, so the overall function is going to be larger. So this function is larger than that. And this is convenient because it allows you to replace this by something that makes it easier to work with. So instead of minimizing this, we're going to make the inequality a little bit less tight. So it would be tighter if you kept it the way that it is. Unfortunately, if you try to solve this directly for lambda, it's not going to be that easy. It's more convenient to make it a little bit less tight so that you can solve it exactly. So this is going to be bounded by, this is bounded by e to the lambda squared over 2 raised to the n over e to the lambda n epsilon. And then if you put everything together, this is e to the lambda squared n over 2 minus lambda n epsilon. So this is what we get. And now we're going to minimize. The idea here is we're going to choose lambda to minimize this function. How do we minimize a function? Well, that's up to you to figure out. So homework. Find lambda, which makes this minimum. And then you're going to substitute that choice of lambda into the function to get, and if you do it correctly, you would get that the probability of the thing that you want, so maybe I should write it out. So this is an bigger than or equal to epsilon, is dominated, and if you choose the appropriate choice of lambda, you will get that this is dominated by e to the negative n epsilon squared over 2. Okay, so if you do it correctly, that is what you would get. So you would get 1/2 of the inequality, and then the other half follows by symmetry, and that's why there's that factor of 2. So that's the way you do it. That's the way you get this much improved, much tighter bound on the tail.